Okay, welcome. Yeah, we just learned the fundamental theorem of calculus, which is amazing. And you did this homework. Let's go over it right now. It contains not a lot of deep stuff, but some interesting things to talk about. Okay, here we go. Number 5. The very first problem says, find the integral from 0 to 1 of 2x. Okay, well, first of all, I don't need the fundamental theorem of calculus for this problem at all, because this is a line and this function is a line, and so I can just draw it. It'll be 0, 0. When I plug in 1, I get 2, and so what we have is a triangle, and so to the extent that the integral is just the area under the curve, this is certainly going to be 1. I want to say right now. And of course, then we could also, since this is a polynomial, we could have done this with Riemann sums, and we would have also gotten 1. But with the fundamental theorem of calculus, we now can say that this is now just a formulaic problem if I know an antiderivative of 2x. And I do know an antiderivative of 2x. X squared is one of those antiderivatives. And so the answer to this problem is just going to be x squared evaluated at 1 minus x squared evaluated at 0, so that's just 1, so that's it. Okay, that was kind of almost like too boring to even be worth talking about. Let's go on to the next one, number 11. Okay, integral from 0 to 1 of 2t minus 1 squared dt. Okay, well, this is getting a little bit more exciting. It's a quadratic, so prior to taking this course, you would probably not be able to find the area under this curve, because this is a curve in which, okay, let's see, no, that's not true. What I was doing there, let's see, when I plug in 0, I get 1, and wait, what's going on here? This is like having when you plug in a half, you get 0, so, yep. And by the time I plug in 1, I get 1 again. So, okay, I guess it's just this. And so the area that I want is the area under this parabola. Yeah, that looks about right. With a vertex at 1/2 and value 1 at 0 and at 1. Okay, well, no, that's just wrong what I said. Second try. When I plug in 1, I get... No, that's right. Okay, anyway, I could probably figure this out by being smart and doing some fancy things like from last week, but never mind all that stuff. The point is, I want a function, f, and what I want that function to have is the property that the derivative of this function is 2t minus 1 squared. And so really what I need to do is to anti-differentiate 2t minus 1 squared, and okay, let's just do this one maybe in our head. We could use substitution, or we could just do it. If you anti-differentiate, what are you getting? You get some kind of cubic, right? So it's going to be 2t minus 1 cubed over 3, but then that's not quite right because there's also a chain rule, so this is going to be over 6. Okay, is that correct? I guess it just is, right? Because if I differentiate this, what happens? The 3 comes down, cancels the 6, leaving a 2 in the bottom, and then 2t minus 1 squared back inside 2. So this is just right. So if I'm getting very good at anti-differentiation, or if I'm very good at anti-differentiation, then now you see why we have been doing this for hours and hours over the past 2 weeks, is because this integral problem can, via the fundamental theorem of calculus, be computed using an antiderivative. And so what we get is that the solution to this problem is just 1/6 2t minus 1 cubed, evaluated at 1 and 0. In other words, I reach for one of the many antiderivatives of 2t minus 1 squared, and there it is. Okay, so let's see, being a little careful now, I get the 1/6 when I plug in 1. Here I get 1, and when I plug in 0, I also get 1. What am I doing? Sorry, when I plug in 1, I get 1, and when I plug in 0, I get -1. Yeah. So, yep, that is right. Because when you cube -1. Okay, so then the answer to this is just going to be 1/3. And I guess that's not a total surprise for various reasons. Okay, it looks about right. Because each of these, well, okay, I'll just leave it at that. Whew, that was number 11. Going too slow, let's go faster. 15 is the integral from 1 to 4 of u minus 2 over root u. Okay, and now you see that it's very, very convenient at this point to be some kind of expert on antidifferentiation. And, well, I am. Because I can reduce this to be I'm going to split this up into two terms because I have a monomial in the denominator here. So u over root u is u to the 1/2, and minus 2 over u becomes minus 2u to the -1/2. In other words, I'm writing it in anti-differentiation friendly form so that I may anti-differentiate this. And here we're now leaving the world of polynomials, so these problems are now sort of not doable by Riemann sum. So we're really getting some new abilities here. And now the way that people do this is they simply sort of just anti-differentiate this on the spot. So what is the antiderivative of u to the 1/2? You go up a power to 3/2 and you divide by 3/2, so this is 2/3 u to the 3/2. And when you antidifferentiate u to the -1/2, you go up a power to 1/2 and you divide by 1/2, so it's like multiplying by 2, so that's like minus 2 u to the 1/2. And then all of that gets evaluated at 4 and 1. And so every now integration problem is, via the fundamental theorem of calculus, reducible to an anti-differentiation problem, essentially. This is really just, I think, amazing, right? If I know an antiderivative, then I just have my answer. Okay, anyway, we do it. So let's see, when I plug in 4 here, I get 2/3 times, well, 4 to the 3/2 is 8, minus, and the square root of 4 is 2, so that's minus 4, and then minus, you have to use parentheses carefully, whatever I get when I plug in 1 for u, which is 2/3 minus 2. So what do we get here? 16/3 minus 2/3 is 14/3, and minus 2, so I guess that's 8/3 as my overall answer. Should probably like check these in the back or something. Do I feel like doing that? 1 second. Make sure I'm not making crazy mistakes. For 5 we got 1. Yeah, for 11 we got a third. Yeah, for 15 we got, uh-oh, I did something wrong. What was it? 3/2, number 15, 2/3 they say. Let's see, I made some mistake. Hopefully it was a very small one. Oh, yeah, I just, there was already a 2 here. So when I anti-differentiate 2 times u to the -1/2, I bet this is the problem, I get this extra 4 here. So that was just sloppy on my part, and which means that number is wrong, because when I plug in 4, and then when I plug in 4 I get, so now this is minus 8, and this is minus 2/3 minus, and now when I plug in 1 I get minus 4. So now let's see what happens. I get still 14/3, but now it's minus 4. So there it is. 14/3 minus 12/3 is 2/3. Okay, I'm glad I had a weird sense that maybe that was wrong. Okay, moving on, 23. All right, and sort of right away we get to a problem which, well, okay, let's just do it. The integral from 0 to 3 of absolute value 2x minus 3. Okay, and things are getting kind of complicated now. I guess, to be totally honest, the way I would do this problem is I would not use the fundamental theorem of calculus. I would say, I would draw a picture. And if you draw a picture here, okay, so what is this function? Absolute value 2x minus 3. Well, it's, if I factor out a 2 maybe, then it's absolute value x minus 3 halves. In other words, this is the function which, well, it's just like the absolute value except been shifted horizontally by 3 halves and stretched out by a factor of 2. So if I go to make a picture of this now, at 0 it's 3. Wait a second. Yeah, sure, it just is. Boom, boom, boom. At 0 it's 3. And it's been moved over by a factor of 3 halves. So at 3 it's also 3, but the slope is 2. And so this is honestly a problem that we knew how to do last week. And if I gave you this exact problem last week, this is what I would expect you to do. And so there it is. And now it just becomes a matter of finding what the area of all that red stuff is. This is 3 over here. This is 3 over here. This is 3 halves. Okay, well, this is just clearly half of this 3 by 3 square. And so the answer to this problem is 9 halves. By some, you know, do your favorite geometric argument to convince yourself of this. But how might we do this problem using the techniques that we learned just this week? Well, if you want to use the fundamental theorem of calculus on a problem like this, then you have to be kind of careful because these absolute values are sort of confusing. And if we want to if we want to find the absolute value of some kind of function, really this absolute value is begging us to split this problem up into cases. And so the function, if I were to discuss this function, absolute value 2x minus 3, probably the very first thing I would say about this function is, well, it's a piecewise function really. And when the inside is positive, then in fact it's just 2x minus 3. And when is the inside positive? When x is greater than or equal to 3 halves. And on the other hand, if x is less than 3 halves, then this, by the very definition of absolute value, this is just pre-calculus now, then this is negative 2x minus 3, like that. In other words, the very definition of the absolute value function is that the absolute value of something is that thing if the thing is positive, and it's the opposite of that thing if the thing is negative. And so, if you wanted to do this with sort of algebra, except as opposed to with common sense, then you would take the integral from 0 to 3 of absolute value 2x minus 3, and you would immediately split it up into 2 separate integrals. You would take the integral from 0 to 3 halves of absolute value 2x minus 3, plus the integral from 3 halves to 3 of absolute value 2x minus 3. So that's just splitting an integral up into 2 integrals. So that's clearly fine. And why would I choose these 2 particular intervals to split it up into? Because now I can say that on this interval, the function I'm actually integrating is 0 to 3 halves negative 2x plus 3. And over here, this would just be 3 halves to 3 of 2x minus 3. Okay, so I ran out of space and sort of time and patience or whatever with this problem, so I'll just leave it like that. This is how, in general, you do an absolute value integral. You split it up into subintervals on which we can say for sure what that function is. And then you could use the FTC at this point. But here I just solved it by picture in a couple seconds, so that seems like a better idea. Okay, we are going too slow. Go faster now. Oh, it's eraser. It's terrible. All right. Okay. Good. 33. Good. 33. Okay, now we're getting to some like hard stuff, man. So here we have, well, the integral from negative pi over 3 to pi over 3 of 4 secant theta tan theta d theta. Okay, well, okay, so let's not talk about it, let's just do it. How can we do this integral? Well, I can't very easily explain what this sort of problem is because I don't know how to sketch a graph of secant theta tan theta, at least off the top of my head. But I have some sort of curve. I'm trying to find the area underneath this curve. And yeah, I guess the answer here is just going to be 0. Right? Well, anyway, I guess maybe we just do it. Well, maybe I don't want to do it. Well, okay, let's do it both ways. So first, the mindless way. The mindless way is the fundamental theorem of calculus now tells me that every integral is just immediately doable if you know an antiderivative. Do you know an antiderivative of 4 secant theta tan theta? Well, yeah, I do, because I just have memorized all my derivative rules. The derivative of secant is secant theta tan theta. And therefore, the function for secant theta is a function which, when differentiated, gives you that. And so the answer to this problem is just going to be this, right? It's just going to be the 4 secant theta evaluated at pi over 3 and negative pi over 3. Okay, so now when I go to actually do this, what is secant of pi over 3? It's like 1 over cosine pi over 3, so this is going to be 2. And then minus, what's secant of negative pi over 3? It is also going to be 2, because it's just the reciprocal of cosine. These have the same cosine, pi over 3. Yeah, pi over 3 and negative pi over 3 both have a cosine of 1/2. And so, alright, just as I predicted, the answer to this problem is 0. So what does that mean? Well, okay, how did I sort of know that in advance? I knew that in advance because I know that secant theta is an even function. So secant theta is even is a fact. In fact, it's kind of almost lame to draw the graph even because the proof of this is just based on the unit circle. So if you give me some kind of theta and you give me some kind of negative theta, then they just have the same cosine and therefore they have the same secant is one way of putting it. So that's just a fact. But of course, tan theta is odd, as we all know, and a similar picture will suffice that if this is theta and this is negative theta, that now we are taking well, y over x, and in this case it will be positive, and in this case it will be negative. The same numbers but opposite. Okay, this is a very long-winded way of saying if secant is an even function, it is. Tan is an odd function, it is. Then the product of an even and an odd function will be odd. And so it's just a fact that for secant theta tan theta is odd. And if you give me an odd function and you ask for the integral from negative pi over 3 to pi over 3, then I can just guarantee that that's going to be 0. I guess we could even just do it, right? If you plug in pi over 3, what do you get here? Tan of pi over 3 is root 3. And secant of pi over 3 we said was 2, so you just get like 8 root 3, right? Up here, oh man, this is way too long of a video. And when you plug in negative pi over 3, you're going to get negative 8 root 3. And so, I don't know exactly what this secant theta tan theta function looks like, but it's going to be positive between 0 and pi over 3, negative between negative pi over 3 and 0, and it's an odd function, and so this interval is just guaranteed to be 0 before I even do any math. But I also could do this, if you change these numbers to be something different, I also know how to do this, because I know the antiderivative for secant theta, tan theta is secant. Okay, good. 35. Okay, 35 is exciting. It says, what's the integral from 0 to 2 of 2 to the x plus 6? Cha-cha. Okay, I don't know why I would necessarily maybe care about this function, but I can graph it. When you plug in 0, 2 to the 0 is 1, so this thing starts up here at 7, and by the time I get to 2, it's not much bigger. It's going to be 10. Okay, so good. Right? Yeah, 2 squared, 4%. So we have some kind of exponential type thing, and so the area we want is this area. If we want to think about this integral as a geometry problem, we want this area between 0 and 2 under the 2 to the x plus 6 exponential function. Okay, and here, I mean, it would be just hopeless for us to try to do this without the fundamental theorem of calculus. If you go back to what we were doing a week or two ago, and you would try to apply those same principles, you know, split the interval from 0 to 2 up into subintervals, take a sample point, you know, make a rectangle, or whatever, you can do all that stuff. You know, delta x would be 2 over n, because we have an interval of width 2 and we have n subintervals. Okay, and I can write what the ith, the sample point on the ith subinterval, if I'm using Rm, will be, you know, 2 over ni, but that is what's being plugged into my function. And so, okay, this is me just sort of going through the logic of what I would do if you gave me this exact problem a week ago. I would do this. And so what we would end up with is the sum from I equals 1 to n of, and now this is like 2 to the 2 over ni plus 6 quantity times 2 over n. So that's completely intelligible. But now I'm just, well, actually, as I say this, I realize that maybe I could do this problem? No, come on. No, jeez. No, I just can't. I don't have a formula for, well, I could try something. I'm actually now slightly intrigued about I've never even thought to consider doing this problem any other way. Maybe you might be able to make some progress using some kind of sum of a geometric series argument or something like that. But okay, never mind all this, because now we are in the golden age in which we have the fundamental theorem of calculus. And the fundamental theorem of calculus says doing this integral is trivial if you know an antiderivative of 2 to the x plus 6. Do we? Yeah, I think we do. 1 over ln2 times 2 to the 6th plus 6x is an antiderivative. That is a function which, if you differentiate it, the derivative of 2 to the x is ln2 2 to the x, boom boom, and the derivative of 6x is 6. That is a function which, when differentiated, is our function. And so if I want to know the area under this function, I just plug in 2, and I get 4 over ln2 plus 12 minus whatever I get when I plug in 0. When I plug in 0, 2 to 0 is 1, so you gotta be a little careful there. You need to get 1 over ln2 plus 0. So distributing the parentheses, I guess what I get is 3 over ln2 plus 12. Now I'm doubting myself on that, but I bet that's right. Yeah, there's a baby crying. 5, 4, 30, 5, 50, 5, 3 over, oh man, no, 35. 3 over ln2 plus 12, yeah. And the previous one was 2. Okay, good. Good. Okay, more. 40, let's just finish this all right now. Okay, boom, boom. All right, this one is not in the back. Let's just sort of push on. What is number 40? Number 40 says take the curve y equals 1 minus x to the fourth. And they even make a picture of this for us. And we're going on the interval from -1 to 1. So here's -1, here's 1, and there's 1, and function looks like this. Okay. Whew. Shouting and screaming. So let's do this. In other words, compute the integral from -1 to 1 of 1 minus x to the fourth. Okay, a couple comments to make here. First of all, it is a polynomial, so I could do this problem. Yeah, I could do this problem by hand, so to speak, without the fundamental theorem of calculus. Let's just do the problem. This function is even, and it seems silly to keep doing this over and over again, but this is an even function, and this sort of is important to kind of learn these sort of shortcuts, because negative numbers are annoying and whatever. And so I think what they really want you to do here, this is what I'm going to do, is to immediately recognize that really this is going to be just twice the integral from 0 to 1 of 1 minus x to the fourth. And alright, I guess I'll just mindlessly solve the problem. How do we mindlessly solve the problem? Well, what's an antiderivative of 1 minus x to the fourth? Antidifferentiating polynomials is quite easy. It's going to be x minus 1/5 x to the fifth. Boom, boom, 1, 0. And now we just do it. We get 2 times, when you plug in 1, you get 1 minus a fifth, and when you plug in 0, you get all zeros. And so what we get is just 8/5. Just bam, right away. 4, yep. Okay, and should we say anything more about this, or just move on? Maybe just move on. 1/5. Yeah. I could sort of tell that was just going to be the answer. Well, I'll just move on. Alright, 46. 46 says, find the area of the region bounded by the graphs of these equations. So we have y equals 1 plus cube root x. It's the same problem, but now there's just no picture. X equals 0, x equals 8, y equals 0. X equals 0, x equals 8, y equals 0. Okay, so I guess it's convenient to make a picture of this. Here's y equals 0. X equals 8. Well, when I plug in 8 here, I just get 3. When I plug in 0, I get 1. So this is just the cube root function, but moved up 1. So what's it going to look like? It's going to look like, I plug in 1, I get 2. So just something like that. And we want to know this integral. Okay, again, I'm so just kind of tempted to talk this out using geometry. I could do this problem without the fundamental theorem of calculus, but, whatever, man. We can just do this now, so we just do it. What do we want? We want the integral from 0 to 8 of 1 plus cube root x. And so what is this? I'll take a moment. Well, I won't even take a moment. I'll just do it. Antiderivative of 1 is x, and the antiderivative of x to the 1/3 is, you go up a power to 4/3. So this is going to be 3/4 x to the 4/3 is certainly correct. If you differentiate this, you get back to cube root. And so, bam, that is one of the antiderivatives of 1 plus cube root x. We evaluated at 8 and 0. And when we evaluate it at 8, we get 8 plus, what is 8 to the 4/3? Well, the cube root of 8 is 2. To the 4th power is 16. So divided by 4, so this becomes 12. And then these are just all zeros. And so this answer is just 20, which looks about, ballpark right. Because this is an 8 by 3 rectangle. So it seems very reasonable that our area is 20 out of that 24 possible. Okay, 4 more, because I already made a video last year going over the last problem, number 109, which I think is really important. This homework is a little bit boring. I'm going to be honest with you. Alright, maybe it gets a little bit exciting in these last couple of problems. 49. Okay, here we have y equals 4 over x, and we're doing it between the curves given are x equals 1, x equals e, and y equals 0. Okay, so just to make a picture of this, e, huh? Okay, so when I plug in 1 here, I'm going to get 4, and when I plug in e, I get 4 over e, so whatever that is. So there's 3, so I get, whatever I get. But the 4 over x function looks like that, and I'm going simply from 1 to e. And so the region being described is this one. Okay, so the geometry here is sort of irrelevant. Really what we just need to do is we need to find the integral from 1 to e of 4 over x. And this is quite interesting. I definitely didn't know how to do this until this week. What should we do? Well, do we know an antiderivative of 4 over x? Yeah, we just do. It's 4 ln x. And so this is just 4 ln x evaluated at e and 1. And so this becomes 4 times ln of e is 1, and ln of 1 is 0. So this is just 4. That's all I have to say about that. Okay, 52. Okay, now we get into some sort of so basically this entire homework so far has just been doing